Okay, so good morning, everyone, and thank you for inviting me as a keynote speaker. It's a pleasure to be speaking at the Microbiome Cozy. All right, so in the past decade, we know that the long read error rate had been between 5 to 15%, which had made it impossible to distinguish closely related haplotypes during genome or metagenome assembly. But now the availability of long and accurate reads has changed the equation. Particularly, if we look at 2020 onwards, the advent of PacBio Wi-Fi sequencing, which provides long read accuracy of about 99.8% and N50 of about 10,000 base pair. And now the Nanopore is also catching up. So we have with the R10.4 protocol, we expect accuracy of about 99% and N50 of above 40,000 base pair for human genome sequencing. Now, this is really remarkable because now we can think of doing diploid, polyploid, and assembly of microbial community while separating closely related haplotypes. So if we look at a very high level overview of the algorithms of assembly, so what we are doing is we are doing long accurate sequencing of homologous chromosomes, right? And the nice thing about these accurate reads is that once we construct the assembly graph, the haplotypes appear as separate paths in these graphs. Because of the high read accuracy, we can observe alternate paths in these string graphs, and using more data such as Hi-C or parental data, we can get fully phased assembly as output. So this affects, not only this enables deployed assembly, human genome assembly at scale, but it has implications for metagenome assembly as well. So recent publications have taken advantage of PacBio and Nanopore sequencing to get high quality metagenome assembly as well. Now, if we look at the graph theoretic models for genome assembly, we know three popular graph structures, right? So the first is De Bruijn graph. So if we use the input read set R, in the De Bruijn graph, vertices are all distinct substrings, also referred to as schemers, of course. And the edges implies suffix-prefix overlap of length k-1 in a De Bruijn graph. Now, in overlap graph, on the other hand, vertices are the input reads themselves, and an edge implies an exact suffix-prefix overlap of length greater than or equal to k. So k is a parameter that we are using here in the subscript. And yeah, so edge implies an exact suffix-prefix overlap of length greater than or equal to k. Finally, the third type, string graph, can be seen as a subgraph of the overlap graph. So we start with the overlap graph, but it so happens that overlap graphs tend to contain a lot of false and redundant edges. So string graph prunes, sparsifies the graph and creates a subgraph of overlap graph, which is subsequently used for genome assembly. So let's see how this graph sparsification is done to construct a string graph. So string graph, as I said, is a subgraph of overlap graph. It was introduced by Myers in 2005, right? So these are the following graph pruning steps that we do to construct the string graph. First is that we only keep the longest suffix-prefix overlap between a pair of reads. So that is first. The second step is that we will remove contained reads. For example, if you have two reads and the shorter read is a substring of the longer read, then we will remove the shorter read from the dataset. The third is the transitive edge reduction step, where suppose you have three reads, as shown in the example here. So if you have three reads, and if you draw the overlap graph corresponding to them, you will find that the connection between the first and third read is redundant, and one can spell the equivalent string graph by going from first to second to third vertex. So accordingly, the third edge, so this particular edge of overlap of length 4 is removed because this is redundant. Right, so right now, rather than going from first to third directly, we will go from first to second to third. So this helps in cutting down the count of edges and vertices in the graph. And this structure plays a fundamental role in many long-read assemblers. The examples include HiFi ASM, Falcon, Raven, etc. Now, just to see a quick example of overlap graph, here I've shown you just a toy example containing 6 reads. And accordingly, each vertex corresponds to a read, and the edges corresponds to overlap of length greater than or equal to 4. Because here I'm showing you the overlap graph while allowing minimum overlap length 4. Now, this is the same graph drawn for our simulated reads extracted from E. coli genome. So this is illustration using 20x simulated long reads from E. coli genome. So N50 here for the simulated reads is 39 kilobytes square. And the overlap graph is drawn with edges representing suffix-prefix overlaps of length greater than or equal to 1000. So you see that the graph is not clean. We don't observe a clean assembly in this graph because, as I said, overlap graphs contains a lot of redundant and false connections in it. So if you see the number of vertices, it's about 4,000 vertices, and we have about 35,000 edges in this graph. Now, if we start constructing the string graph and we execute the step of removing contained reads, we see a remarkable cleaning of the graph. So now you see a clean thread in the graph, and the vertex count reduces to 159 only, and the edge count reduces to 528. So I hope you appreciate that how much the graph classification is important for long read assembly. But still we observe that if you take a look at any of these vertices, still we have more than one incoming and more than one outgoing edges, which is still not good because that creates ambiguity during genome assembly. So the next step would be to remove transitive edges. And once we remove transitive edges, you get a clean assembly with 159 vertices and 158 edges to connect all these vertices. So you can see through this example how important graph classification is for long read assemblers that use overlap layout consensus approach. Now, the question that we are addressing here is that suppose I give you sufficient sequencing coverage over a particular genome, do we have a guarantee that all chromosomes can be spelled as walks in the graph? So this is a fundamental guarantee that we would like to ensure. So if there is sufficient sequencing coverage, at least the chromosomes should be spelled as walks in the graph. It may not be a non-ambiguous walk, it may be ambiguous walk, but still they should be spelled as walks in the graph so that there's no information loss happening. Now, to answer this question, first I need to convert this question into a well-formulated problem. Because so far I've not described you what do we mean by sufficient sequencing coverage, right? So let's start with converting this question into a well-formulated problem. Okay. So the first assumption we will make is that the genome is circular, right? So the true genome is assumed to be a set of circular strings. Each circular string represents a chromosome sequence. And we will assume that there is some upper bound known for the chromosome length, and we will denote it using phi. So here is a toy example showing a genome with 2 chromosomes. TATAC and TACGTCGT. A read will be then a substring of one of these circular strings. So here TAT is a read that is sampled as a substring of chromosome 1. Now, what assumption do we want to make on sequencing coverage? So informally, what we want to have sufficient coverage over a circular string Z, we want to ensure that the reads should cover Z, right? So the read should cover the entire circular string. And the suffix-prefix overlap between consecutive reads should be above a certain threshold. So the suffix-prefix overlap length between consecutive reads should be above a certain threshold, right? So this is the minimum guarantee that we need for the sufficient sequencing coverage assumption. So to formally put this, we can state this in the following manner. So there exist parameters L1 and L2 such that L1 is less than L2, and all intervals of length L1 minus L2 in circular string Z include the start of at least one read of length greater than or equal to L1. Now so I'll help you understand through an example. So suppose this is a circular string, right? And we would like sufficient sequencing coverage over the circular string. So let's say the parameters L1 is 4 and parameter L2 is 1. So I would like to look at all the intervals of length 3 on this circular string, and each interval should include the start of at least one read of length greater than or equal to 4. So if I use the read ACATG and second read as ATGA, then my sufficient sequencing coverage assumption is satisfied, because all the 5 intervals include at least start of at least one read of length greater than or equal to 4. So there is one technical catch here. So just to make this definition mathematically precise, technically a read can map to multiple locations in a genome. So rather than saying that it includes the start of at least one read of length greater than or equal to L1, we will say that it includes the start of at least one substring of length greater than or equal to L1 that matches a read belonging to R. Right? So now the definition of sufficient sequencing coverage is defined, but still this quotient falls short of being well-formulated problem, because we have still not defined what true chromosomes mean. We would like to ensure that the true chromosomes can be spelled as box in the graph, but how do we define these true chromosomes? Because the input to our problem is the read set, and we don't know these chromosomes a priori. Now, defining this precisely is not difficult, because what can happen is there can be multiple assembly candidates as output, which are possible from a single input. For example, again, if you see these two reads, TATACA, and the second read, you have two assembly candidates that are possible from this read set. So rather than saying that true chromosomes can be spelled as box in the graph, what we will try to say is all the possible assembly candidates that are possible from the given input should be spelled as box in the graph, because we don't know which of them is true. So here's the definition. So given read set R and all the parameters, C denotes the set of all candidate assemblies which satisfy the coverage assumption. And then we will say that the graph G is said to be coverage preserving if and only if all the candidate assemblies can be spelled as a closed box in the graph. So now this question becomes well formulated, and we can ask whether existing graph models are coverage preserving or not. So for example, again, if you have two reads and these parameters, then from these reads, we know that CATGA is a candidate assembly. So for the graph G to be coverage preserving, it must spell this candidate assembly as a string walk in the graph. Now, we gave following theoretical results in our work. So the input again is the read set R and the parameters L1, L2, and 5. So we proved that the De Bruijn graph and overlap graph models are coverage preserving for given parameters, but the commonly used string graph model is not coverage preserving for any value of k. So in other words, the De Bruijn graph and overlap graphs are guaranteed to be coverage preserving if there is sufficient coverage over the genome. But in the string graph, we are not guaranteed this property. So the proof techniques that we use to make these claims, but for the De Bruijn graph, we prove this claim by contradiction. For overlap graph, we prove this claim by giving an algorithm that will compute a closed walk for a given candidate. And for the string graph, we only need to give a counter example that shows that string graphs are not coverage preserving. The limitation of string graphs was first highlighted in an earlier paper by Hui et al. In 2016. Yeah. So this limitation of string graph has been known before. So in the next couple of slides, I want to summarize the proofs techniques that we use to make these claims. So the first claim is that the De Bruijn graph is coverage preserving for all values of k less than equal to L2 plus 1. So if as long as the k-mer size used for De Bruijn graph construction is less than equal to L2 plus 1, the De Bruijn graph is guaranteed to be coverage preserving. And the proof is rather simple. So here we say the proof is by contradiction. So we will assume that there is a candidate string Z which is not spelled by the De Bruijn graph. So suppose Ki denotes the k-mer starting from position I of string Z. So in this figure, the red line, the red curve denotes the k-mer I. And consider the minimum I for which the k-mer I, ki, is missing in the De Bruijn graph. So let this k-mer let this I be the minimum I value for which this k-mer is missing in the De Bruijn graph. Now we can directly say that this cannot happen because if you look at the interval just before position I, based on our coverage assumption, there must be a read that starts in this interval. And that read is guaranteed to have k-mer I in it. So this violates the assumption, and therefore the De Bruijn graph is guaranteed to be coverage preserving. So next, for the overlap graph, we have to be slightly more careful because the vertex labels in overlap graph are of variable length, and the suffix prefix overlaps are also of variable length. So here, to prove that overlap graphs are coverage preserving, as long as the minimum suffix prefix overlap length is less than equal to L2, we give an algorithm. So if you give me a candidate circular string, I will identify a closed walk in the graph that will spell Z. So for this, the algorithm works in the following way. So for a given circular Z, string Z, I will look at all the intervals of that string. And from each of these intervals, I will pull out the reads that are used to satisfy the coverage assumption. So these are all reads of length greater than or equal to L1 that start in these intervals. And from them, I'll carefully identify a subset of these reads such that these reads adjacent have a suffix prefix overlaps, and they are guaranteed to form a closed walk in my graph, which will spell the circular string Z. So a more formal detailed proof is available in the preprint, but here just is a high-level sketch of how the proof works. Finally, the third type, string graph, as we said, is not guaranteed to be coverage preserving. And here is a simple counterexample to show that string graphs are not coverage preserving. So assume you have 4 reads, right? So I'll label them as blue, red, green, and purple. And from these 4 reads, we can identify 2 candidate assemblies. But it turns out, if you closely look at this, so the red read is actually contained in the green read. And we know from the string graph sparsification rules that the contained reads will be removed during the graph construction. So what that means, if I remove my red read, I won't be able to cover the first candidate genome assembly anymore. So this example clearly shows that a coverage gap is introduced when contained read is removed. And despite having sufficient coverage over the genomes, we still don't have guarantee that there will be walks that spell these genome assemblies. So this analysis leads to following questions. So is there an alternate method to sparsify overlap graph that is practically efficient and provably good? I mean, we have seen in the previous examples that overlap graphs tend to be very big, and graph sparsification is very important. So we cannot ignore the graph sparsification. That has to be done. But is there a way that is practically efficient and provably good? Can we have good heuristics to recover non-redundant contained reads, the contained reads that are actually useful to cover the genome? And finally, do these questions matter for long read assembly in practice? Because string graphs are actually being used by the latest assemblers available today. So do these coverage preserving properties matter in practice? So we will see that. So first, I want to show you that we try to come up with safe theoretical rules that would help us sparsify overlap graphs. So first, of course, rule is very simple and intuitive to understand, that we can remove a vertex or edge from the graph if the set of circular string walks remains unchanged. So as long as all the circular walks in the graph remain unchanged, I can remove a vertex or an edge iteratively. And a transitive edge reduction by Myers is an example of this edge removal. So during the transitive reduction, we ensure that the string walks are conserved. The second useful property is that removing a contained read is safe if we know that it maps to only a single candidate circular string at a unique location. So again, this result is intuitive, because if you imagine there are, let's say there are multiple candidate assemblies, but the contained read only maps to a single candidate, then we know that the parent read Y, which actually contains X, will also map to the single candidate exactly at that location. So even if we remove contained read X, still parent read Y can support the coverage at that region. So in that case, it is safe to remove the contained read. So now the next question is, can these be implemented efficiently? Unfortunately, the first and third rules, we don't know of an efficient algorithm to implement them. Because in the first case, in fact, we have to enumerate all possible string walks to check whether a vertex removal or edge removal is safe, which is computationally expensive. And for the third rule, actually, we need to know all the candidate assemblies. Again, which is not efficient algorithm to compute those is not known. But however, the good thing is that the transitive reduction of course, from Myers is very efficient, and that is usually realized in practice because it is polynomial in time doable. So given the challenges in implementing these optimal rules, next we look for heuristics. Can we have heuristics inspired by these rules, which we can implement in a software and test? So the first heuristic that we test is inspired from the previous rule that we just discussed. So during genome assembly, we always do all versus all read alignments. So from the all versus all read alignments, we can guess if a contained read maps uniquely within a single haplotype. This can be done. So if we imagine you have all versus all read overlaps, and let's say we have a contained read. Now, if you look at the overlapping reads and you see that there is a site, there's a position in the contained read which supports two heterozygous, which has a heterozygous site, and you detect the presence of a heterozygous allele at this position, and we check that the pileup size of the alignment is within the coverage range. So if this is observed, then we know that this contained read should map uniquely within a single haplotype. So this heuristic can be used to detect redundant contained reads. The next heuristic that we propose is based on K1 assessment. So here we check whether a contained read leads to a novel walk. So to do that, we say, okay, so we will extract a set of all k-mers observed within bounded length string box in the assembly graph from the contained read. And we will also look at the set of all k-mers from the bounded length string box from its parent reads. If the set K1 is observed to be a subset of K2, then we can estimate that all the k-mers that are appearing from contained read are also appearing in the vicinity of parent reads. So again, this is used as a heuristic to estimate whether a contained read is redundant or not. So if it is found to be redundant, we remove this contained read from the dataset. So using these heuristics, we implemented a prototype implementation. So what it does is it takes long reads as input and all versus all read overlaps. At the first step, we discard the contained reads which have heterozygous variants. Second, we build the overlap graph, apply transitive reduction, edge reduction from Myers, and then again apply the KMR assessment to further reduce the count of contained reads, and finally output the set of non-redundant contained reads as output. And we hope that in this process, the large fraction of contained reads is thrown away so that we can sparsify the overlap graph as much as possible. So let's see how this works in practice and how the benchmark numbers look. So to evaluate, what we did is we simulated error-free reads with Nanopore and HiFi specific length distributions. For haploid genome, we took CHN13 sample from the telomere T2T consortium. And for the diploid genome, we took a HG002 diploid assembly from HiFi ASM QO method. So the haploid genome is sampled with 20x coverage. So the Nanopore N50 is 40,000 base pair. For HiFi, the N50 is close to 20,000 base pair. For diploid, we sample reads at 15x coverage per haplotype. So that makes it 30x coverage total. And again, the N50 is about 40 and 21,000 base pair for ONT and HiFi respectively. So let's first see how many coverage gaps are caused if we directly remove the contained reads as done by the string graph formulation. So it turns out that for the haploid genome assembly, actually removing contained read does not lead to any coverage gaps. So if we look at the estimated count of contained reads in these two datasets, it's 3.1 million in the ONT and 1.9 million in the HiFi haploid dataset. And in this case, it turns out that the coverage gaps are not introduced by removing the contained reads. However, if we move to the diploid datasets, where there is a more risk of losing haplotype specific information, here we see that removing contained reads leads to 46 coverage gaps in the Nanopore dataset. The properties of these coverage gaps are here. So the mean length of coverage gap is 11,000 base pair, and the maximum length of coverage gap introduced is 53,000 base pair. The coverage gap is assessed by pulling out all the contained reads and then mapping the non-contained reads back to the haplotypes. So if there is no coverage loss, then we will see the entire complete range of genome mapped with the reads. But if there are intervals in the genome which are not mapped, then we know that there's a coverage gap introduced. For HiFi, we observe only a single coverage gap. Again, mean length is about 2000 base pair, and because it's only one, so mean and max is same. Now, this is expected that for diploid genome assembly, the coverage gaps are introduced, and for Nanopore particularly, the coverage gaps are higher than HiFi. And the reason is that if you look at the read length distributions in Nanopore and HiFi respectively, the read length distributions in Nanopore is highly skewed, as we know. So as you know, the number of reads reduces with the read length in Nanopore dataset, whereas the distribution is tight and follows almost like a normal distribution in HiFi. So the chance that a particular read is contained in a longer read is much higher in Nanopore, and that is why we see more coverage gaps in case of Nanopore data. So before I show you the results of our heuristics, here's a quick look at the existing methods. So as I said, the paper from 2016 was the first to observe this limitation in string graph, and they identified a heuristic to retain the useful contained reads based on the read overlaps. So they said that a contained read is removed if it is contained in two reads that are inconsistent with each other. So by inconsistent, I mean that if you look at the two reads that are containing a particular read, then they're inconsistent if they mismatch at a particular position. And that makes sense because if they mismatch at a particular position, then they likely spell two haplotypes. So in that case, it's a reasonable heuristic that the contained read can be removed, because no coverage loss should happen if two haplotypes are spelled by other parent reads. HiFi ASM also implements a heuristics to retain useful contained reads, and it does recover contained read after the graph construction. So in HiFi ASM, a contained read is recovered if it is seen to join a broken haplotype walk. So here, just as a toy example, again, if you see two walks and one of the walks is broken, then it attempts to rejoin a walk using contained reads. And from that, if a contained read helps to join a walk, then it will recover that read to make two paths again. So here are the results. So I tested 4 methods. So the first method is retain all, which basically means that I retain all the contained reads. Second heuristic is by the 2016 paper. The third is basically I remove all contained reads. And fourth is containx, where we try to carefully pick contained reads which we find to be useful. Now, the columns here are showing the count of contained reads retained. Then the count of junction reads. These are the reads which have either more than one incoming edges or more than one outgoing edges. So higher number indicates more ambiguity in the graph. And finally, what is the count of coverage gaps remaining after retaining the contained reads? So as we would expect, the retain all method would of course retain all the contained reads, and the count of coverage gaps caused will be 0. But if you look at the graph, the count of junction reads is massive. And this means that the graph has become very ambiguous by retaining all the contained reads. Similarly, if you look at remove all heuristic, then of course all the coverage gaps are introduced now, and the graph is simpler because the number of junction reads is much less. The method in 2016 paper tends to be also very conservative in the sense that it retains most of the contained reads, and the count of junction reads is almost as high as it was with retaining all the contained reads. So in our method, we find that we retain 28,000 contained reads in this ONT dataset, and the count of junction reads is much lower than what it would have caused by retaining all the contained reads, but it's a little higher than removing all the contained reads. And here we see that reduction from coverage gap from 46 to 2. So here what we see is that by carefully selecting contained reads, the coverage gaps have reduced without affecting the graph complexity dramatically. Similarly, in HiFi, where we only saw one coverage gap, we see that similar performance where ContaiNX method retains a fraction of contained reads, and the junction reads is a fraction higher than removing all contained reads. So there is increase in complexity of the graph, but not a dramatic increase in the complexity. So HiFi SM is also tested here. So if we look at HiFi SM, which is a full-fledged assembler, we are finding that the heuristics are not working in the sense that 35 coverage gaps are still observed out of 46 in HiFi SM for Nanopore. But for HiFi, it resolves the single coverage gap that was observed. So the conclusions of this work are as following. We saw that overlap graph and De Bruijn graph models are guaranteed to be coverage preserving, but the commonly used string graph model is not. The sparsification of overlap graphs in assembly is important, but the optimal sparsification of overlap graph still remains unsolved. Here in this work, we discuss safe rules and some promising heuristics to carefully select a subset of contained reads. We also saw that ignoring contained read leads to coverage gaps during assembly of reads, which have skewed read-led distribution, such as of Nanopore. And we believe that this will likely have even more impact on samples which have less heterozygosity and high ploidy. So the preprint for this work is available online, and we have all the prototype software is also available online. So please feel free to test it. I leave with some open questions here. So with the advent of long accurate reads, can we investigate assembly algorithms that are both provably good and practically efficient? Second, is optimal sparsification of overlap graphs a tractable problem? And third is contained read removal is just one of the many heuristics that long read assemblers use. So it will be good to have a detailed theoretical and empirical analysis of all those heuristics to see their impact on the assembly quality of diploid polyploid genomes as well as assembly of microbial communities. And in particular, how much do these assembly heuristics affect accuracy in medically relevant loci of the human genome, where the accuracy is of high importance. So with that, I'll close the presentation. Thank you for your attention. I'll acknowledge Hawen, Mile, Robert, Brian, Sergey, and Hayu, who provided useful feedback for this work. And finally, funding sources, ISA, DST, and NERSC for resources as well as computing resources. Thank you all for your attention.
Thank you, Dr. Jain. I think we have time for a couple of questions. I don't see any from the online audience. Any question from the in-person ones? I'll start with one, Dr. Jain. So for string graph, what is the computing complexity, and do you think it's feasible for like terabase metagenome scale, yeah, terabase scale assembly?
Yeah, so string graphs are scalable, definitely for deploy. So I can tell for deployed genome assembly, for example, if you look at Hi-Fi ASM software, for Hi-Fi reads, it does the computation in about 6 to 7 hours. So, and with respect to scaling, the biggest computational overhead is computing all-to-all read overlaps. So as long as we can compute all-to-all read overlaps, I think we can scale. But yes, all-to-all read overlap computation is the bottleneck. So that needs to be scaled even to terabase size data sets.
Yeah, I mean that's all is like n square, right? That's might be a problem for if you have too many reads.
It's not, so n square is when we compute it exactly, but with the heuristics, so typically use seed and extend based methods to compute these read overlaps. So it's also a function of, so empirically we have to see how the runtime scales, but it may not be quadratic in terms of the size of the data. It depends on the composition of the data as well.